we are studying transformers, and essentially a transformer is a pair of coils. Okay, let me draw two coils, and suppose the number of turns is N1 and N2. Okay, here are the primary terminals and here are the secondary terminals. Also, I need to put dots to make it complete. And now suppose L1 is the self-inductance of the primary coil and L2 is the self-inductance of the secondary coil, and suppose M is the mutual inductance between the two coils, and suppose primary current in this direction is I1t, function of time, here I2t, secondary current, okay, and similarly the voltage on the primary side is V1 plus minus, function of time, and V2 is the secondary voltage plus minus, like this. Okay, so here I have shown all the voltages and currents as functions of time. Correspondingly, so V1, V2, I1, I2, etc., they will be the corresponding phasor values. Okay, so we are assuming that all voltages and currents are varying sinusoidally, so the corresponding phasors are denoted with uppercase letters with a bar above. Achha. And yeah, one more thing, say R1 is the resistance of the first coil. A coil is a conductor, most often copper, so it has some resistance, although we normally use a very thick copper so that the resistance is very negligible as possible, but still it's not zero. Okay, similarly, suppose R2 is the resistance of the secondary coil. Okay, now what will be the value or expression of voltage V1? What can we write? V1 will be equal to I1 R1, that's the voltage drop due to the coil resistance, plus I1 multiplied by j omega L1, that is due to the self-inductance, but this is not complete. There will be one more term due to the secondary current, okay, due to the mutual inductance. So how much will be that? So that will be j omega M multiplied by I2, and should the sign be positive or negative? That we get from the dot convention. See here, current I2 is entering the dotted side. That means for the voltage, if I write M di2 dt, which is induced in the primary coil, that will have its positive polarity towards the dotted side, okay, because the other current is entering the dotted side. So that's why here we should have plus. Okay, now you can guess, you can understand that if I change the direction of I2 or if I change the position of the dot, then this plus here it can become a minus. But for this particular circuit, this is plus here. Okay, so I may also write the same equation in this way as a function of time, V1t, so that will be I1 R1 plus I1 d, L1 d I1 dt plus M di2 dt. Okay, so whenever we write an equation containing functions into its corresponding phasor form, Simply all ddt terms get replaced by j omega. That's it. So similarly, for the voltage V2, how much will that be? That will be I2R2 plus I2 j omega L2 plus j omega m I1. Okay, so is it fine so far up to this? Are these two equations okay? Do you follow?
Yes, sir.
Okay. Now, Now, so this is a transformer, but when we talk about an ideal transformer, okay, suppose I have an ideal transformer with the same turns ratio N1 is to N2, and if these are the dots, this is an ideal one, and suppose here is the current I1, here is the current I2, and and here is the voltage V2 plus minus, V1 plus minus. What is the relation between these voltages, among these voltages and currents? Okay, for an ideal transformer, the relations are V1 by V2 is N1 by N2, and I2 by I1 is N1 by N2. So that's the case for an ideal transformer. Now the question is, are these same? Are these same? You can readily see, I mean, possibly you can guess that these are not same. So these are not same, not exactly same. Now, what we want to do is that, okay, we want to model this circuit, the left side circuit, we want to model as follows. Okay, so I will take an ideal transformer with the same turns ratio in 1, in 2, dot, dot, okay, here, yeah. Now, this ideal transformer together with some impedances, okay, connected in a particular fashion like this. Okay. So what I want to model this actual transformer under consideration as an ideal transformer in combination with some impedances connected in a particular fashion. Call it Z1, whatever you like, Z1, Z2, Z3. Okay, and we want such that this ideal transformer together with this impedance should behave like this transformer. They should be equivalent. Okay, so these two, so I can also write that, or I mean model it as, or I mean these two should be equivalent. Basically, my task at this point is to find out the value of Z1, 2 and 3 such that these two circuits are equivalent. Okay, so find Z1, Z2, Z3 such that, okay, let me give some name. Let me call it circuit A, and let me call it circuit B. Okay, so I have to find Z1, 2 and 3 such that A and B are equivalent. That is the task. Now how can we do that? Okay, so for before that, let me also give some names to these terminals as A, B, C, D. Here also I have the same names A, B and C, D. Now when I say that these two circuits are equivalent, if so, then when seen from outside of any of these circuits, they should behave identically, they should behave equivalently. Okay, so now in this circuit, if I call this so this voltage should also be V1 plus minus the phasor value. Okay, so maybe I should also write here the phasor values to be consistent. V1, V2, I2 and I1. So here also I should have the same currents I1, I2 and same voltages V1, V2 plus minus. Okay. Now for this second circuit, circuit B, what are the relations between these voltages and currents? So from B, what are the relations between V1, V2, among V1, V2, I1 and I2? Before that, if I call these two terminals as E and F, then how much, let me, I have done one mistake. Okay, there is one mistake here. The mistake is that in this equation I should have a minus sign here. Okay, because for an ideal transformer, if one current is entering a dot, then another current should actually leave the dot, so that their MMF can cancel each other. Okay, so here I should have a minus sign. Okay, fine. Achha. Now, yeah, okay. Fine. Achha. Now consider this ideal transformer part. Okay, if this current is I2, how much should be this current? Anyone? This should be I2 N2 divided by N1. Correct? So let me just call that N1 by N2 is equal to A in short. Okay, so that this will become I2 by A. And then how much is the voltage between these two terminals here? If the secondary voltage is V2, then how much is this voltage? That's V2.
V2 into A.
V2 into A. Absolutely right. Okay. Now consider the left side part of this circuit. Okay, that means this impedance part. And from here, I want to write the expression for the voltage V1. What should be the value of V1? So I1 is flowing here, and the current here is I1 plus I2 by A. Okay, so how much is the voltage from here to here? That should be, just apply KVL. It will be I1 plus, I1 into Z1 plus Z3 plus I2 by A into Z3. Am I correct? Please check once. I1 plus into Z1 plus 3, I2 by A into Z3. Yeah, looks correct. Fine? And similarly, now look at this voltage V2 and apply KVL, add up the voltages here. So then this voltage AV2, that should be equal to, just apply mesh rule, so it comes out I2 by A, Z2 plus Z3, and plus I1 into Z3. Okay, could you please check once? If I have a mistake later, I will have a severe problem. I hope it's correct. Okay, so now let me write this as V2 equal to I2 Z2 plus 3 divided by A square plus I1 by A into Z3. Okay, let me give some equation numbers. Okay, so suppose this is equation number 1, 2, 3, and 4. Now we want this circuit B and circuit A to be identical, to be equivalent. Okay, for that what we need? We need equation 1 to be identical with equation number 3. Okay, expression of V1 should be identical for these two circuits. Similarly, equation number 2 should be identical with equation number 4. Right, that's what we want. Now let's see what do we get from there. Okay, so comparing equation number 1 and 3, look at the coefficient of I2. Okay, here the coefficient of I2 is j omega m, and here the coefficient of I2 is Z3 by A. Okay, so that means Z3 by A should be equal to j omega m if these two equations are identical. Let me just take this A on this side, A j omega m. Okay, so that is one thing we get. Next, can we similarly find out the values of Z1 and Z2? Say, consider the equation 1 and the coefficient of I1. What is the coefficient of I1? That is R1 plus j omega L1. Okay, so R1 plus j omega L1, that is the coefficient of I1. And similarly in equation 3, the coefficient of I1 is Z1 plus Z3. Okay, so we have Z1 plus Z3 equal to this. So from here, we get the value of Z1 equal to R1 plus j omega L1 minus Z3. I need a bit more space. And Z3 is A j omega m. Okay, so that's the value of Z3. Sorry, Z1. Similarly, this is the value of Z3. In the same way, can we find out the value of Z2? Okay, so for that, let us consider equation number 2 and look at the coefficient of I2. Okay, that is, coefficient of I2 is R2 plus j omega L2, And in equation 4, that means the equation of V2, the coefficient of I2 is here. So Z2 plus 3 by A square is this. Okay, so from here we get the value of Z2 equal to A square R2 plus J omega L2 minus Z3, which is here, minus AJ omega M. Okay, so that means Z2 is A square here, A square, let me take that common, R2 plus J omega L2 minus J omega M by A. So that's the value of Z2. So what does this mean? It means if I take the value of Z1 like this, Z2 like this, and Z3 like this in circuit B, then circuit B will act identical to that, identical to circuit A. Okay, so let me make a copy. So this transformer is equivalent to this one So these two are equivalent with Z3 equal to how much? A M J omega. J omega A, let me get some space. M, okay, and similarly Z2 is A square R2 plus J omega L2 minus J omega M by A, okay, that is this impedance, and this one is Z1, which is R1 plus J omega L1 minus A J omega M. Okay, so this is called an equivalent circuit of an transformer. This is called more precisely the equivalent circuit referred to primary side. Okay, this is called the equivalent circuit referred to primary side. Why primary side? Because to model this transformer, we have considered an ideal transformer with some impedances connected on the primary side. That's why it is called an equivalent circuit, referred to primary side. Now, one thing you have to understand, I guess you know that equivalent circuits are never unique. Okay, so this is a general note that equivalent circuits are not unique. What do I mean by that? And for example, if I say that a 10 ohm resistance is equivalent to two 5 ohm resistances in series, so this is an equivalent circuit, but this is also equivalent to say two 20 ohm resistances in parallel, and you can find out many other combinations of resistances and maybe also other things which are also equivalent to this 10 ohm resistance. Okay, so equivalent circuit is not unique. What does it mean? It means one circuit which behaves identical to the original circuit as seen from the outside world. Okay, so here also if you look at this circuit from outside, that means from terminals AB and AB, CD, and in this case also if you look at it from outside, that means from terminals AB and CD, they will behave identically. Okay, any questions so far? Anyone? Acha. Now,
No, sir. All good.
yeah. Now let me tell one more thing. There, I mean, as you can guess, if there is a circuit called equivalent circuit referred to primary side, then there should be another circuit which is called an equivalent circuit referred to the secondary side. Okay, so how will that look like? So that will look as follows. Oof. We will have one transformer and we will take some impedances connected on the secondary side. In this way, like a T, 3 impedances connected like a T, or this is also called the star. Okay, and now these are the terminals A, B, C and D. Now this impedance, if I write it as Z4 is, and if this is Z5 and if this is Z6, okay, they in general are different from Z1, 2 and Z3. How much should be the value of Z1, Z4, Z5 and Z6 such that this circuit, call it circuit number C, find out the value of values of Z4, 5 and 6 such that circuit C and circuit A, they are equivalent. How to do that? You can once again follow this procedure as we did. Just write the equations relating the voltage and currents and then compare the equations. That is one way of doing it, as we already have done. But there is a shortcut way, okay? Because we already know the solution for this. I mean, what are the requirements for this to be equivalent to the original one? Now we also want that this circuit C to be again equivalent to circuit B and circuit A. Okay, so what should be the values of Z4, 5 and 6? Anyone? In our Tuesday's class, we told this that you can transform voltages, currents and impedances from one side to the other side. And I mean, like in this case, you see that basically this Z1, 2, 3, this structure is here on the left side of the transformer, but here the same structure is connected to the right side, secondary side of this transformer, and the transformation rules are Z4 should be equal to Z1 multiplied by N2 by N1 whole square. Okay, similarly Z5 should be equal to Z2 times N2 by N1 whole square and so on. Z6 should be equal to 3 times n2 by n1 whole square. If I take these values, then this circuit will also be equivalent to the previous two circuits. Now, this is called the equivalent circuit referred to the secondary side. Now I have a question. Suppose this is the equivalent circuit of an actual transformer. Now let me ask the question that when will this transformer behave like an ideal transformer? Under what condition this equivalent circuit will be similar to an actual an ideal transformer? When? What should be the value of Z1? What should be the value of Z2 and Z3, so that this total circuit is just an ideal transformer? The answer is we need Z2 to be equal to 0, Z3, Z1
0.
also 0. So Z1, Z2 0, and Z3
Infinite, very large.
Yes. So that's what we need. Okay. Now let us check how to get these conditions. Okay. Now Z3 tending to infinity implies what? What can be infinite here? Z3 is j omega am. What can be infinite? So we need basically m tending to infinity, very large practically. And m is what? M is approximately equal to, what is the expression of m? N1 N2 by reluctance square, reluctance of the core, and which is basically which depends on the permeability of the core. So we need this permeability to be very large. So recall that was one of our assumptions for an ideal transformer. Okay, so that is one thing we need. We need very high permeability core. Secondly, now then consider Z1. How much is Z1? This is R1 plus j omega L1 minus a j omega m. Now for this to be equal to 0, what do we need? Number one, R1 should be 0. That means the resistance of the coil should be very small. That is another assumption required for a transformer to behave ideally. Okay, so coil resistance 0, practically very small. What else? Now notice that note that this quantity j omega common, and then we have L1 minus am. Okay, this is approximately equal to j omega. How much is L1? L1 approximately we estimated this to be N1 square divided by the reluctance of the core, and A is N1 by N2 and M is N1 N2 by reluctance. So this is 0, fine, approximately this is 0. Okay, but practically L1 is not N1, I mean by reluctance of the core, and I mean this is not exactly 0 practically. Why? Let me tell that. Okay, so this is not exactly 0. Why? Let me tell it here. Okay, so consider an transformer with 2 coils now. When there is some current flowing here, what happens? This coil produces some flux which mostly pass through the core because the permeability of the core is very large, but there is also some flux which go through the air or partially through the air like this. Now let me call this flux as phi m, which go through the core, and this flux which go through the air is phi l. Since mu of core, permeability of core is very high, that's what we assume is very high, that means phi m is much larger than phi l, and therefore in calculation of inductance or voltage we can ignore phi l. We do ignore phi l. Okay, so phi l is called the leakage flux. That's for your information. However, phi l is not 0. Now what happens? When I calculate, say, L1, the self-inductance of coil 1, I should actually consider both phi m and phi l. But if you recall the way we did it earlier, we considered only this core flux phi m. Okay, we didn't consider phi l. Okay, so therefore L1 will be actually larger than what we estimated previously. Okay, so L1 will be larger than what we estimated previously, and therefore in this equation L1 will be larger, and this quantity won't be exactly 0, this will be some non-zero quantity. Okay, so this won't be exactly 0. Now when will it be close to 0 or approximately equal to 0? Only if this phi l is very negligible compared to phi m. Okay, under that situation this term will be 0. So therefore this term j omega L1 minus Am, this is called the leakage impedance. And it will be equal to 0 if the leakage flux is much smaller compared to the common flux or core flux, mutual flux, which goes through the core. Okay? Achha. In the same way, similarly, okay, for this transformer, this circuit to behave like an ideal transformer, we also need Z2 to be equal to 0. Okay, so similarly, we also need Z2 equal to 0, but Z2 is equal to this quantity. Okay, yeah, let me write here a square R2 plus j omega L2 minus j omega m by a. Am I correct? Let me check. Yes. Now, for this to happen, what do we need? Once again, we need R2 to be equal to 0. That means the secondary coil should also have negligible resistance, and what else do we need? This L2 that should be equal to m by a. Okay, is it true? Now if I take so we know that L2 is approximately equal to N2 square by co-reluctance, and M is N1 N2 by co-reluctance. So and A is N1 by N2, so if I use these two approximate equations, okay, these two equations will imply this to happen. Okay, but these two equations, they are only approximately true. Why? Once again, the reason is that now if you want to calculate the L2 of the second coil, okay, we should also consider any flux that goes through the air. Okay, call it phi L2. Okay, so this phi L2 together with phi M both will induce voltage in coil 2. But if you recall, when we did previous approximate calculations, we assumed that most of the flux goes through the core. So phi M is a much larger quantity than phi L2. So we ignored phi L2, and from that we got these two approximate equations. But actually, L2 will be larger because this phi L2 should also be considered. Okay, so therefore, actually, this term here won't be exactly 0, but okay, this is close to 0. Okay, so yeah, is there any question so far? Anyone?
No, sir.
Okay, fine. Then, so what? Okay, the essence. Let me just summarize. What we have said so far. An actual transformer, I will write it as TFO in short, is more or less always equivalent to the following circuit, where basically this circuit. Okay, where here we had j omega m, so that means basically a coil with inductance M, okay, and here we had Z1 was equal to R1 plus some j omega times something, okay, so this is a resistance plus some inductance term, okay, so one coil, okay, so R1, and let me call it X1, okay, then similarly Z2, this is also equivalent to one resistance together with some inductance, call it R2, and JX2, okay, this is also JX2, okay, so where we call R1 as the primary coil resistance, R2 is secondary coil resistance, and X1 is called primary coil leakage impedance, and X2 is secondary leakage impedance. M is called the magnetizing impedance. Okay, fine. Next, any questions so far? No. Okay, so next we will learn that if somebody gives me an actual transformer, you might have seen transformers on roadsides. Okay, so somebody gives me an actual transformer and I want to find out experimentally what are the values of this R1, R2, X1, X2, M, etc. Okay. Oh, acha, before that I have to tell one more thing. One more thing. Let me tell in this way. So in our last class, we solved one example problem with an ideal transformer with 3 windings. Okay, so let me copy this. Okay, let me make it a bit clean. Okay, now suppose N1, N2 and N3 are the turns ratios, number of turns actually. Achha. Now, and this is an ideal transformer for simplicity. Okay, so that means coil resistance 0 and leakage flux going through the air is negligible. Okay, and the permeability of the core is very high, tending to infinity. Now, this is an ideal transformer. This is equivalent to this circuit is equivalent to the following one. If I take 2 ideal transformers, one with N1 and N2 turns, another is with N1 and N3 turns. Okay, and here the dots were like this on this side and on this side. Okay, so I take the dots like this, and now what I do, here I had the source. I connect the source to both the primaries. Parallelly. Okay, okay, so they are getting the same supply, right? Okay, yeah, so here if this is V1, I have V1 here plus minus, here also V1 plus minus, correct is my diagram. Yeah, and then here I connect R, if this is R1 and R2 or whatever it may be in general, Z1 and Z2, I put Z1 here and Z2 here. Now, if you think for a while, you will realize that these two circuits are equivalent when this transformer is ideal. Okay? Okay, let me just keep R here, R1 and R2. Now, next, you have any question here? If not, next what I will do is this. So, consider say this upper transformer part. Okay, just consider this part. Okay, so I replace this part here with one resistance of value R1 multiplied by N1 by N2 whole square. Then this is also equivalent as seen from the source side. Okay, so this is also equivalent, and now very simply speaking, so this is equivalent to source, then here N1 is to N3, R2. Okay, where should be R1? I mean this resistance in this circuit, that is here. Okay, if I call this R1 prime, then this is R1 prime. So it's a transformer with 3 windings in this way is equivalent to a single transformer with 2 winding and one impedance is brought to the primary side like this. Okay. So do you follow this up to this? Okay, I mean you need to actually go through the Tuesday's class to follow this better. Okay, fine. So now next one more thing I am going to talk about is eddy current loss or eddy current in a transformer. Okay, so consider a transformer this is the core. Now I have, let me put first one winding and I haven't put the second winding yet. Now if I apply a voltage here, this behaves like an inductor only. Now what happens? It will create flux. How will the flux lines be? Okay, so let me draw only in this part. The flux lines are like this. Okay, and they are also varying with time. The magnitude is varying. Okay, so it may become positive or negative, but this is the path approximately. Okay, so here also we have it. And so on. Now, there is no secondary coil. but this core is normally made up of some iron or iron alloy, so this is also a conductor. The core is a conductor. Okay, so maybe now if you consider this right side part of this core, okay, so here we don't have the secondary coil yet, but this itself is a conductor. So you may imagine, say, a path round this core. Okay, so imagine a closed path like this. Okay, now, so this is also a conductor, and this is also closed. Okay, so even if there is no other coil, there will be some EMF induced in this closed path. Okay, and if there is some EMF induced, there can be some current. Okay, so we may have some current flowing in this closed path like this. Okay, so can you imagine the path that I am talking about? And there is not just one path, there are many other such paths. For example, this path you can consider. Okay, or you may consider a path, closed path here. Okay, all these virtually behave like secondary coils. Although there is no actually secondary coil, but the core itself behaves like a secondary coil. Okay, so all these paths everywhere, I mean not just, I mean here also you can find a secondary closed path like this here. Okay, so all these closed paths behave like a secondary, behave like secondaries, many secondary coils. Okay, and these currents which flow inside the core in circular paths, okay, these currents are called eddy currents. These currents inside core is called eddy current, and what is the effect of such current flowing in the core? What effects can you think of? Number one, current is flowing, so there will and the core has some resistance, so there will be some I square R loss, Joule heating. Okay, and so the effect of Joule heating is what? Number one, where does that heat energy come from? That must be coming from somehow, in some way, from the source. Otherwise, where is it drawing the energy from? Okay, so that means even if there is no secondary coil, current is flowing inside the core, causing heating and wasting energy. So that is one. So that way energy is lost. That is one bad effect. Secondly, the temperature of the core will also increase, and if it increases significantly, that will slowly damage the insulations and other other windings, etc. Okay, so that is the harmful side of this eddy currents flowing in the core. Now, how to prevent eddy current? How can we prevent this? How to prevent eddy current? The answer is as follows. Okay, so what we do, let me copy this once again, and let me make it slightly cleaner. what we do is this: we do not make the core by a single metal piece, by a single iron piece. Instead, we make it by joining many small iron pieces, basically small slices. We call so the slices are actually like this. Okay, so I will cut this core like a bread. You can think in this way. Okay, so let me cut out one slice. Okay, so this part of this portion. Okay, that means here also, yeah, this portion is one slice. Okay, next consider another slice which is like this. Okay, so that is the second slice, and then consider another slice, maybe this part. Okay, and all these parts are joined together, and these individual slices are called stampings. These are called stampings. Now I have drawn these stampings to be quite thick, but normally these stampings are, I mean, this thickness, okay, is only a fraction of a millimeter. Thickness is about a fraction of a millimeter. So that means you may have to stack or collect hundreds or thousands of such slices to construct the core. And all these slices or stampings, they are insulated from each other. That means this green line that I have here, this green line is an insulator. Okay, so that means this orange slice and this white slice, they are not connected electrically. They are insulated from each other. Okay, so stampings are insulated from each other. Okay, so here are the insulations. Now, what is the advantage of having these insulations in between? If you see this previous diagram, okay, what is the path, prospective path or potential path for the eddy current to flow? So those are like circular or closed path in this way. Okay, so here also you may imagine a closed path. Okay, like this. So this is a closed path through which the current will try to flow. Okay, but you see, there is, I mean, this closed path is not electrically closed because there are insulations in between. So this way, the resistance of this closed paths is increased to a very large extent, and therefore the amount of eddy current is I mean, lower to a very small amount. Okay, so now if eddy current wants to flow, it actually cannot flow in this closed path. If it at all has to flow, it has to flow only in this smaller, I mean, in this within one slice only. It cannot go from one slice to another slice. Okay, so this way the eddy current is reduced, correspondingly heating is reduced, and energy loss is also reduced. Okay, so any questions so far? Is it okay? Any question? Anyone? Yes?
No question, sir.
Okay, fine. Acha. Now, when we derived the equivalent circuit of a transformer, okay, so while doing this, so we started from these equations. In these equations, we are considering non-zero coil resistance R1, R2, okay, and we are, here we are nowhere considering anything like permeability to be very high or not. So many non-idealities like non-infinite permeability, non-zero coil resistance, these things are all modeled in these two equations. But one thing, I mean, actually there are many more things which are still missing, which are still not modeled in these equations. One among those missing things is eddy current. Okay? So while writing these equations, eddy current is not considered anywhere, or while deriving this equivalent circuit, we haven't talked about eddy current. So now let me, so far we have found this or this here, this one, as the equivalent circuit of an actual transformer without considering the eddy current loss so far. Now, if we also consider eddy current loss, how should this equivalent circuit to be modified so that it can also incorporate, it can also model eddy current loss? What do we do? Let me just make a copy. Okay, now to also model the eddy current loss or eddy current, we modify the equivalent circuit as follows. Okay, so this was the circuit before without eddy current. Now we can put maybe one resistance here. Why? Why? Because in this circuit, now if I put a secondary coil, let me put it here. Now I have one primary, but how many secondaries are there? Anyone? In this, one secondary is here, but other than that, these closed paths, they also act like secondary, which we cannot neglect. Okay, so that means there are one actual secondary and many virtual secondary you can call, which are eddy current paths. Okay, so at least there are two types of secondaries. Okay, and then we saw that, yeah, in this example, if we have multiple secondaries in a transformer, that can be modeled like, we can keep one secondary as it is, and other one we can model it by transforming the impedance of this or the resistance of this secondary to the primary side. Okay, so in that way, similarly, if I consider this eddy current secondaries, and if I want to model it, I have to put one more resistance to the primary side. Okay, approximate, and now the question is whether it is here or exactly where to put it. I will not go into that detailed analysis because I'm not at this point. I don't want to go into more detail. Okay, so I will just put one more resistance here. Okay, call it R0. R0 models the eddy current effect. Okay, and this becomes one circuit which will more or less represent the actual behavior of an actual transformer. Okay, an ideal transformer for which V1 by V2, I1 by V1 by V2 equal to N1 by N2 equal to I2 by I1, that does not represent an actual transformer very well. But this circuit with proper values of this R1, R2, X1, X2, R0, M, this will better represent an actual transformer. Okay, so this better represents the behavior of practical or actual transformers. Okay, maybe I should call this also X, because X, let me call it XM, because I'm calling this X, so to be symmetric, I mean, let me call it JXM. Okay, maybe here also I should call it JXM. Okay, so this is XM. Okay, so yeah, again, the main thing I want to convey you is that this circuit will better represent an actual practical transformer with, I mean, for some suitable values, or for suitable values of R1, R2, X1, X2, XM, R0, etc. Okay, that is the main point. Now, one more thing I want to say is this. Okay, so for a good transformer, how much should be the value of R1 and R2? Should it be small? Should it be large? For a good transformer which behaves like an ideal transformer, more or less like an ideal transformer, how much should be R1, R2, X1, X2? For good transformer, yes, R1, X1, R2, X2 should be
Zero.
Zero, as small as possible. Okay, ideally 0, and R0, XM, that should be large as possible. Okay, practically what I mean, it is like this: R1, R2, they may be just a fraction of a ohm, whereas this R0, XM, they may be hundreds or thousands of ohm practically. Okay. Acha. Then yeah. Now, under the assumption when R1, R2 are X1, X2 are small and R0, XM they are large, then this circuit is also equivalent to this one. Here this is R1 plus R2, and here it is X1 plus X2. Okay, what I have done, I have just taken the small impedance from here to the right side. Okay, this is also equivalent, and similarly I can also do this. I can take this right side impedances and put it on the left side. Okay, so this is R1 plus R2 and this is jx1 plus x2. Okay, this will also be equivalent under the assumption. Okay, so let me call these circuits as what can I call P, Q and R. Okay, circuit PQR, circuit P, Q and R are approximately equivalent, approximately identical, equivalent if R1, R2, basically I mean this thing. Okay, if the series impedances are very small and these parallel impedances are very large, okay, then these three circuits are also equivalent. Okay. Do you see why is that so? Okay, so it may take a while for this to realize. In fact, it may take longer time to actually prove it mathematically. What I mean, they are equivalent, or how much approximation I have done, so that to tell that more precisely, more mathematically, will take much longer time. But one thing you see, okay, if here the voltage is V1, and tell me how much is the current, total current through these parallel branches, approximately. Who will tell me quickly? If this voltage is V1 and R1, X1, these are small, how much is the current here through this parallel branch, total current? Here. Anyone? That will be V1 divided by R0 plus JXM. Why is that so? Because the voltage drop across R1 JX1 is small, so therefore the if I call this terminal as A, B, C, D, E, okay, terminal E and A, they are practically at the same voltage because R1 X1 is small. So now consider this second circuit. Now in this circuit, how much is the current through these two parallel branch? Again, V1 by R0 plus, this current, what I have written here. Okay. So basically here there is no voltage drop, and here the voltage drop is small. Small is negligible. In that sense, these two are equivalent. And in the third circuit, okay, if I consider how much is the voltage drop from A to E, again that is small because R2 is also small, X2 is also small. Okay, so that's why these three are equivalent. Now, one more observation, okay? One more observation. If this current is I1, and if this current, in these two branches, is, call it I0, let me write it up. Let me write it here. If this is I0, okay, then let me ask how much is the voltage drop in this part across the series impedance? Approximately, what will you say? How much is the value of I0? I0 should be ideally small. Okay, I0 should be ideally small because R0 and XM is large. Okay, so if I0 is small, then the voltage drop in this part, I can write it approximately as I1 multiplied by R1 plus R2 plus JX2 plus JX1 plus JX2. That's the voltage drop here. In this circuit also, it's the same. Approximately they are same. Here also it's the same. Okay. So that's why we take these three circuits to be equivalent while solving questions or problems related to transformers, because sometimes you may find that okay, it is easier to solve the second circuit compared to the first circuit maybe, and since it's a small approximation that is allowed, there is no much harm. Okay. So what we call is this, we call this first circuit as exact equivalent circuit. The second circuit is called approximate equivalent circuit. Yeah, I mean refer to primary because all the impedances are on the primary side. Okay. You can also consider the same thing for this impedance is considered on the secondary side of the transformer. That you can also do. Yeah, and the third circuit is also called approx equivalent circuit. Okay. Actually, the first one is not exact. There are many other things which we are not considering here, like capacitance of interturn capacitance. So, but okay, but this first circuit is very close. I mean, it is very close to an actual the behavior of an actual transformer under normal operation. Okay, comparatively, the second and third circuit is little far, little more approximation is there, so that's why we call it approximate equivalent circuit. Okay. Yeah. So any questions so far? Anyone? No. Okay. So next we shall talk about estimation of transformer parameters. I mean equivalent circuit parameters you can say. Okay, transformer equivalent circuit parameters. I mean the estimation of R1, R2, X1, X2, R0, Xm, etc. That means if one transformer is given to me, okay, and I know the turns ratio same, but I do not know these parameters R1, R2, X1, X2, etc. And I want to find out these parameters experimentally. Okay, so experimental estimation. How to find these parameters experimentally in laboratory or in on site. Okay. Acha. Now, so we will perform two experiments, two tests, which are called open circuit test and short circuit test. That's our next topic. Okay. So for that, let me copy this. Okay, sorry, not this one. Just a second. Let me take the second one. Actually, I mean, the procedure that I am going to tell you, through that, it is not possible to determine R1 and R2 separately, X1 and X2 separately. Okay, that's difficult. It's not easy to separate R1 and R2, X1 and X2 through the process that I am going to tell. Rather, we will find out R1 plus R2 together and X1 plus X2 together. Okay. So let me take the second circuit. Okay, maybe it's better if I just clean it up a bit. So here I have call it R prime. Okay, so this is equal to our previous R1 plus R2, and call it X prime, Jx prime. So that is equal to our previous X1 plus X2. And this here we also had the resistance. This is Jxm, this is R0. Okay, acha. Then now, acha, let me ask you first. Let me see whether you can tell me some procedure. Suppose here this transformer is not there. Okay, suppose this transformer is not there and this is directly connected. Okay, under that simple situation, when this ideal transformer is not there, okay, if I just give you this part of the circuit, okay, acha, maybe I copy it. Okay, and so this circuit is inside a box. Okay, R prime X prime, this is C D. You cannot open this box, but without opening this box, by doing some experiment from outside, can you find out the value of these impedances? Let me make it more simple. Let me make it little more simple. I just write this as Z prime, one impedance, and here Z0. Can you find out Z prime and Z0 from outside without opening the box? You can do any measurement from outside. Any suggestion? Let me ask, if I measure the impedance between node A and B, okay, so impedance from here, somehow, maybe I connect a voltmeter, a voltage source, and okay, so I can do this, take a voltage source, connect it here, okay, then measure the voltage, also measure the current. Okay, this is approximately, I mean, I'll do more precisely, but later. From here, can you find out the, any of these internal impedances from, if I measure the impedance from outside between A and B, how much will that be? How much is the
Z0?
Z0, when the C and D are kept open. Okay, if I keep secondary open and measure the impedance between, from here, ZAB, call it ZAB. Okay, so then ZAB should come out to be equal to Z0. So in this way I can get Z0. Now similarly, can I somehow get Z prime? Any suggestion? Okay, there may be many possible ways. One possible way is this. I sort A and B and I measure the impedance ZCD. CD, so seen from, here. Okay, so for that I will again connect a voltage source and I measure the current. Okay, so what will be the value of ZCD? Yes?
Will be Z primes.
Z prime. So this way we can get Z0 and Z prime. That is the basic philosophy. That is the basic idea. Now, so that's the basic idea. Okay. Now, let me tell in more detail. Okay, so that's the basic idea. Now what I will do is this. Okay, I connect a source, then an ammeter. I may need more space. Ammeter, then an wattmeter. And a voltmeter. Okay, this is a wattmeter. Actually, we are going to do open circuit test, and for this we are going to keep C and D open. Okay, now from this, so we know wattmeter reading W is known. Okay, so readings of wattmeter, ammeter and voltmeter are known, are seen. Then from that, can we find out the value of R0 and JXM? This wattmeter is measuring which power? Power consumed where? Acha, before that, okay, so here the impedance between C and D is how much? Z equal to infinite. So if I call this A and E and F, how much is the impedance between E and F? Infinite multiplied by N1 by N2 whole square, that is again infinite. So impedance between E and F is again infinite. That means E and F are practically open. Okay, so here E and F are also open circuited. Okay, so if so, that means this portion of the circuit you can forget, it's not there. So now, who is consuming power in this circuit? Where is it consumed? it is consumed by the resistance R0. And how much is the power consumed by R0? How much is the voltage across this resistance? That is V, reading of the voltmeter or the supply voltage. Okay, so I can write power consumed by R naught, that is equal to V square by R naught, and that is equal to W, the wattmeter reading. From this, you can find the value of R naught. So this will give the value of R. This gives the value of. Let me write. This gives R naught. That will be equal to V square by W, wattmeter reading. Okay. Achha. Then, if the ammeter reading is I, if this current is I, how much is I? I is equal to V divided by square root of R0, sorry, not this way, V by R0 square plus V by XM square, okay, and square root of this. Now V is already known, R0 is known, reading of the wattmeter is observed. So from this you can get we can get XM equal to how much? Fine. So you can get the value of XM. Okay, that's open circuit test. Yeah. Now just one note here is that before that, any questions so far? Anyone? Okay. Now, yes. Now, to do this test, okay, how much voltage can we apply here to this primary of a transformer? Can we apply any amount of voltage? No, because all transformers have some rated voltage. We cannot go beyond that voltage. So normally we will do this test normally. The applied voltage is equal to the rated voltage of the transformer. Okay, rated primary voltage or secondary voltage depending on from which side you are doing this test. Okay, so that's one point. You should not apply any voltage larger than that, then the transformer is just gone and it may cause also dangerous accidents. Okay, fine. Next, we shall talk about short circuit test. Okay, and now let us do this as follows. You can do it, you can do this test in different ways. Okay, let me do it in one way first, and if time permits, I will tell different ways of doing it. Okay, so I says, sort the terminals A and B. And between C and D, let me connect an ammeter, wattmeter, okay, this is the current coil, this is the pressure coil. In the previous diagram also, I forgot. Anyway, from the symbol you can recognize that this is the current coil because this has less number of turns, so less impedance. And this is the potential coil, pressure coil with more turns, denoting these more turns are drawn to indicate more impedance. Okay, so here an wattmeter, voltmeter, and a supply. And A and B are sorted together. Okay. Now, if so, the wattmeter will give you some reading. Now, who is consuming that power? Where is that power consumed? Who can tell me? It is consumed by R prime only, okay, because through R naught there is no current, it is bypassed by a short circuit, so R prime is consuming the power. Now, if this voltage is V, okay, if this, let me call this V2 say, okay, if this is V2, then how much is the voltage between E and F? That will be AV2, okay, and if the current here is I, in which direction I don't know because the meter only gives us RMS value, so RMS value of this current is I. If this is I, then how much is the current here? It will be I by A. Okay. So now, how much is the power consumed or wattmeter reading? That will be I by A whole square, I square into R prime. Okay, that is equal to wattmeter reading. And the value of I, current value, is obtained from the ammeter. Okay, so from this we can get R prime is whatever W by I by A whole square. Okay. Now once we know the value of R prime, let us now find the value of X prime. How much is the magnitude of this R prime and Jx prime together? That means R prime squared plus X prime squared, this impedance should be equal to this voltage AV2 divided by I by A. So A is square above. Okay. Now V2 is known, I is known, so our right hand side is known. Okay. So here RHS is known, R prime is known, we already calculated it, R prime is also known. Okay. So from this we can obtain the value of X prime. We can find X prime from this equation. Okay, so that's how we can get X prime. Okay, any question here so far? No? Okay, so then let me tell maybe another, there are different ways in which you can do it. Another way, okay, of SC test. Oh, before that, while doing this test, how much voltage can we apply here? Tell me someone, what do you think? Can we apply rated voltage? Okay, if this voltage is rated, if this is the rated voltage, then how much will be this current? Okay, so if V2 is the rated voltage, then I, this current here, okay, you may call it I2 here also, then I2 everywhere, okay, then how much will be I2? So on the left side of the transformer, how much is the impedance? R prime plus Jx prime. Now if I bring this impedance, if I transform this to the secondary side, then the impedance will be R prime plus Jx prime multiplied by N2 by N1 whole square. So this quantity is the impedance seen from the secondary side. So therefore V2 divided by this, okay, that will be the value of the current. Okay, so this is the value of the current. Now here, if V2 is the rated voltage, the denominator R prime and X prime, that is a small quantity. For good transformer, I told that this impedances R prime and X prime should be small. So therefore, this will be very large. So will be very large. And this will exceed the rated current and it will cause mishaps. Okay, so therefore, SC test is not done under rated voltage. Rather, it is done with rated current, for which we need very low voltage to be applied. Okay, so what we do when we do the experiment, we apply a very small voltage, first very small 0 voltage, then we gradually increase it. We look at the ammeter reading. The moment when the ammeter reading equals the rated current, we stop increasing this voltage, and with that voltage, that will be a very low voltage. With that voltage, the test is done. Yes. Yes. Please repeat.
बस खत्म होने वाली है। भोगड़ी बकचोदी चल रही, नहीं पीटने ठीक है, चल रहा।
Okay, fine. Yeah, so now I'm going to tell you another way of doing short circuit test, which is as follows. Let me take this circuit once again. Previously what I did, I sorted A and B and applied the supply on the right side. Now I am going to do it in the reverse way. I am going to sort C and D. Okay, C and D sorted. And now I apply source voltages. Current coil, pressure coil of an wattmeter. Okay, now Now, when we do this estimation, okay, so C and D are sorted. Okay, so C and D are sorted. So how much is the impedance between E and F as seen from the left side? 0 multiplied by n1 n2 by n2 whole square, that is 0. So E and F are again sorted. Okay, so that when we sort C and D, that means E and F are sorted as seen from the left side. Okay, so this is sorted practically, and then now if this current is I1 has two possible paths, one through this R prime X prime, another through these parallel branches. Now, which path has smaller impedance? R prime X prime, right? Because R0 and Xm, they are very large, therefore practically this current here is 0 approximately. That's what we shall assume for this estimation. Okay, so if this current is 0, then wattmeter reading which is equal to the power consumed. So let me write it as W is equal to power consumed by whom? Consumed by, mostly by R prime. Okay, because through this R0 current is negligible, so that doesn't consume much power. That's what we assume, and this is equal to I1 square R prime. Okay, so this is equal to W. So from this we get I1, we can estimate I1 as W by R1. Oh, sorry, I mean we can estimate R1, R prime as W by I1 squared, right? Achha. Then after that, consider this quantity V by I1, that is the voltmeter reading by ammeter reading. Voltmeter reading, okay, let me call it V1, V1 by I1 by ammeter reading. That should be equal to what? The impedance between A and B. Now the impedance between A and B has two paths. One is this R0 XM and another parallel path is R prime X prime. Now since R prime X prime is much smaller compared to R0 XM, so therefore this impedance between AB, ZAB is approximately equal to R prime plus JX prime, the magnitude of that. Okay, so that means V1 squared by I1 squared is equal to R prime squared plus JX prime squared. Now we already know V1, I1 and R prime. From that we can get X prime. That is another way. Okay, so we can find from here how much is X prime. Oh, J is not here, sorry.